process. The combustion process consists of the oxidation of of constituents in the fuel that are capable of being oxidized and can therefore be represented by a chemical equation. During a combustion process, the mass of each element remains the same. The mass of each element remains the same. Thus, writing chemical equation and solving problems concerning quantities of the various constituents basically involves the conservation of mass of each element. Conservation of mass of each element. Thus, this chapter presents a brief review of the subject, particularly as it applies to the combustion process. Consider first reaction of carbon with oxygen. We say that C plus O2 oxygen and products are CO2. Reactions. Products. This equation states that 1 kilomole of carbon reacts with 1 kilomole of oxygen to form 1 kilomole of carbon dioxide. This also means that 12 kilograms of carbon react with 32 C plus 32 kilograms of O2 will give us the CO2 kilogram of CO2. All the initial substances that undergo the combustion process are called the reactant, and shown also here. and the substance that results from the combustion process are called the products. When a hydrocarbon fuel is burned, both the carbon and hydrogen are oxidized. Consider the combustion of methane as an example again. The combustion of methane. CH4 2A2 CO2 plus 2H2O. Here the product of combustion include both carbon dioxide and water as shown in this reaction. The water may be in the vapor, liquid or solid. Vapor, liquid or solid, depending on the temperature and the pressure of the product combustion. Depends on T and P. In the combustion process, many intermediate products are formed during the chemical reaction. In this book, we are concerned with the initial and the final products and not with the intermediate products. But this aspect is very important in a detailed consideration of the combustion. In most combustion processes, the oxygen is supplied as air rather than as pure oxygen. The composition of air and a molar base is approximately 21% oxygen and 78% nitrogen and 1% argon for air. %21 oxygen, nitrogen, and 1% argon. We assume that the nitrogen and the argon do not undergo chemical reaction. For air, we assume that nitrogen, N2 and argon do not undergo chemical reactions, except for dissociation, which will be considered in Chapter 16. Do not undergo They do live at the same temperature as the other products, however, and therefore undergo a change of state if the products are at a temperature other than the original air temperature. At high temperature achieved in internal combustion engine, there is actually some reaction between nitrogen and oxygen. And this gives rise to the air pollution problem associated with the oxide of nitrogen in the engine exhaust. In internal combustion engine, there is reaction between N2 and O2, which goes to exhaust emission pollution. In combustion calculation concerning air, the argon is usually neglected and the air is considered to be the argon usually neglected and the air is considered to be composed of 20% O2 plus 79% N2. When this assumption is made, the nitrogen is sometimes referred to the atmospheric nitrogen, atmospheric N2. Atmospheric nitrogen has the molecular weight Mn2, which takes the argon into account. Compared to for the pure nitrogen. For pure nitrogen, the distinction will not be made in this text, and we will consider 79% nitrogen to be pure nitrogen. The assumption that air is 21% of oxygen and 79% nitrogen by volumes leads to conclusion that for each mole of oxygen, with this assumption, for air 21% O2 into the for each mole of oxygen into available. Therefore, when the oxygen for the combustion of methane is supplied as air, the reaction can be right. For example, for methane reaction, CH4 plus 2O2 the minimum amount of air that supplies sufficient oxygen for the complete combustion of all carbon, hydrogen, and any other element in the fuel that may oxide is called the theoretical air amount of air that supplies sufficient oxygen for the complete combustion of all the carbon, hydrogen, and any other element in the fuel that may oxide is called fuel that may oxide is called the theoretical air. When complete combustion is achieved with theoretical air, the products contain no oxygen. In this case, the products contain no oxygen. A general combustion reaction with a hydrocarbon fuel and air is thus written as, for example, for a general combustion reaction with a hydrocarbon fuel and air is thus written as follows: CXHY O2 CO2 plus with the coefficients to substance called stoichiometric coefficient. Stoichiometric coefficients VCO2 stoichiometric coefficients are, for example, if we make an equality with different elements, for example, for carbon, C. For hydrogen, two V N2 and for O2 plus which equals to for the generalized combustion reaction, hydrocarbon combustion reaction, and the total number of mole of air for 1 mole of fuel becomes total number of moles of air for 1 mole of fuel in air This amount of air is equals to 100%. And we said the amount of air is equals to 100% theoretical air is equals to 100% theoretical air In practice, complete combustion is not likely to be achieved unless the amount of air supplied is somewhat greater than the theoretical air. The importance parameter often used to express the ratio of fuel and air are the air-fuel ratio AF the ratio of fuel and air. And its reciprocal fuel air ratio. Fuel air ratio FA. These ratios are usually expressed on a mass basis, but a mole basis is also used at times. A fuel mass ratio equals to M air on M fuel and also for the mole basis A fuel mole N air on N fuel. They are related through the molecular mass as related to molecular masses, air fuel mass, M air on M fuel, N air M fuel, M air, N fuel, fuel, M fuel. This is AF mole base multiply to molar mass of air on the molar mass of fuel. And a subscript S is used to indicate the ratio for 100 theoretical air, also called a stoichiometric mixture. Subscript S is used to indicate the ratio for 100% theoretical air. Also called the stoichiometric mixture. In an actual combustion process, an amount of air is expressed as a fraction of theoretical amount called percent theoretical air. Process. An amount of air is expressed as a fraction of theoretical amount called percent theoretical air. A similar ratio named the equivalence ratio equals to the actual fuel-air ratio P actual fuel-air ratio on theoretical fuel-air ratio. Or FA on FAS. Or A air fuel actual. The reciprocal of percent theoretical air. Since the percent theoretical air and the equivalence ratio are both ratio of stoichiometric air fuel ratio and the actual air fuel ratio, the molecular mass cancel out and they are the same whether a mass basis or a mole basis is used. Thus, for example, 150% theoretical air means theoretical means that the air actually supplied is 1.5 times the theoretical air and the equivalence ratio and the equivalence ratio is 2/3. To the complete combustion of methane for this theoretical air can write plus 1.5 theoretical air ratio multiply 2, we can N2 with computing the calculating stoichiometric coefficient, we can obtain these quantities. Having balanced all the stoichiometric coefficients from conservation of all the atoms, the amount of air actually supplied may also be expressed in terms of percent excess air the amount of air actually supplied thus 150% theoretical air is equivalent to 50% excess air. 150% theoretical air equals to 50% excess air. The term theoretical air, excess air, and equivalence ratio are of the kind used to give an equivalent information about the recent mixture of fuel and air. When the amount of air supplied is less than the theoretical air required, the combustion is incomplete. When the amount of air supplied is less than the theoretical air, required, the combustion is incomplete. If there is only a slight deficiency of air, the usual result is that of some of the carbon units with the oxygen to form carbon monoxide instead of, in this case we have CO instead of CO2. If the air supplied is considerably less than the theoretical air, there may be also some hydrocarbons in the product of combustion, or maybe some unburned hydrocarbon. Even when some excess air is supplied, a small amount of carbon monoxide may be present. The exact amount depending on the number of factors, including the mixing and the turbulence during combustion. Thus, the combustion of methane with 110% theoretical air can be right at this equation. For example, for theoretical air, CH4 plus the theoretical air multiplied O2 N2. We have also the material covered so far in this section is illustrated in some examples. In this fractional analysis, after this chapter, we have the enthalpy of formation. Next section is the enthalpy of